All right, y'all. So we're on now on exam 2020, question 2 from 2020 exam 1, right? So this problem does take a little bit of time to do, but once you get the hang of it, it becomes pretty kind of just like repetition. So here we're given a uniform surface charge density rho s0 lies in the xy plane inside of a circular region defined by rho is less than a and phi is between 0 and pi over 2. And the first problem, part A, asks us to find the electric field component, the Z electric. I can barely see this, but this is a Z actually, at the point 00h as shown below. So first, what do we do? I mean, we're given this information. We're asked to find the electric field component. What should be our first step? Well, your first step should be, how do I relate rho, the surface charge density, and electric fields? Now, one thing that might come up is, you're given some charge density. Maybe you use d times the surface area, or the integral, like this ds is equal to q enclosed, and then from q enclosed you find d, and then you solve for e with epsilon. In this case, it's probably not the best way to go about it, as this is, not the type of problem to be doing that. For this problem, we're actually going to be using a specific equation. The electric field is equal to the integral of rho s0. Let me make sure I get this. Oh, I have it right here in mind. Of r, and remember that prime means that is where the charge is at. This is where the charge originates. Divided by 4 pi epsilon naught r squared times the r unit vector ds. This ds will change if you have a linear charge density or if you have a volumetric charge density. This is a surface integral. Now, the first question you should ask here, what is r? What is the r unit vector? Well, r unit vector is going to be equal to the r vector divided by the magnitude of that r vector. Or another way you can think about this is r itself. Now, let's break this up. What is r? The r vector, well, this is x hat times x minus x prime plus y hat times y minus y prime plus z hat, z minus z prime. Remember, this is what? This should be our observer, and x prime should be our charge. Okay, so knowing this x hat doesn't go away. X. Does the observer have an x component? No, it's 0. Does the charge have an x component? Yes, it does. We'll leave it as x prime. Plus y hat. Does the observer have a y component? No. Does the charge have a y component? Yes, y prime. Plus z hat times z. Does the observer have a z component? Yes, it's h. Does the charge have a z component? No, it's 0. So now we have our r vector, negative x prime, or negative x hat times x prime, minus y hat times y prime, plus z hat h. Now, I'm going to do this a little bit of a different way than what the answer sheet says, mostly because this is the way I've been doing it, and so I'm going to stick to this way. And realistically, you can do it any way you want, as long as you get the correct answer. And doing it this way is actually kind of a shortcut, in my opinion, for getting the components, x, y, and z components, because you have a very easy way to, distinguish what's your x, y, and z components. Anyways, now we need to find the magnitude. This is going to be equal to x squared, x prime squared, plus y prime squared, plus h squared. Now we also know x prime squared plus y prime squared is the radius of our circle, which then what we can say is equal to rho prime squared plus h squared. Perfect. Sometimes you can say this is a. In this case, it's actually easier to say rho prime because why? Well, because we're in the cylindrical coordinates. How do I know we're in cylindrical coordinates? I know this because we are given rho, phi, and z. If we were given theta anywhere and phi, well, then I would know we would be in spherical coordinates. But we're given little hints, and this should start becoming kind of like a mantra. Y'all should see this and just know which type of coordinate system we're in. That way you can simplify your math. Okay, so now we found r. This is equal to negative x hat x prime minus y hat y prime plus z hat h divided by the square root of rho prime squared plus h squared. What is another question you might ask? Well, what is rho s at the origin of charge? That's just rho s 0. So what we can then say is E is equal to the surface integral, and remember, surface integral entails that we have a double integral of rho s 0 divided by 4 pi epsilon naught. What is r squared? Well, that's this thing to the power of 2, which is just rho prime squared plus h squared. And rho prime squared plus h squared times something, it's, well, I guess that multiplied by itself, but the other thing is to the power of 1 over 2, so we have rho prime squared plus h squared is equal to r squared, and this is now going to be multiplied times r is equal to r to the power of 3, or rho prime squared plus h squared to the power of 3 over 2. That's what we're going to put here. Hopefully y'all followed that. You will notice that happens very often. And now we can write our top part x prime minus y hat y prime plus z hat h. What else were we missing? We're missing ds. What is ds in cylindrical coordinates on a horizontal plane? Well, you might not need to know on a horizontal plane versus the surface. You will be given it, but in this case, we're given rho and phi. So let's just say this is rho d phi. This is again found in note 6. And again, you have to do primes because we're talking about with respect to the charge. Okay, so now we know we're doing it with respect to rho prime and phi prime. We need to find our bounds of integration. For rho prime, we are integrating from 0 to a. That's on the outside. For phi prime, they give us it in the problem statement, but we can also see here going from x is equal to 0 to y is equal to 0, or x is equal to 0 to y is equal to some number. That's going a 0 to pi halves phi value, and now we've set up our integral. Perfect, we're done, pretty much. Part A, now that we have our electric field, we can do part A very easily. Finding the z component. So what are we going to do? We're going to get rid of the x component, get rid of the y component, only look at the z component. So E of z is equal to the, well, let's see, this here is not dependent on z, so let's just take it out. Or not dependent on z, I mean not dependent on rho prime or phi prime, so we can take it out of the integration. The rest of it needs to stay. One thing we can do, though, is take out the d phi prime, because nothing in our problem depends on it. Another thing, now we can then integrate everything else. 0 to a is going to be rho prime divided by rho prime plus h squared. Again, don't forget the square there. The power of 3 over 2 d rho prime. Let's take this step by step. The integral of d phi prime from 0 to pi over 2 is pi over 2. So we're left with rho s 0, 4 pi epsilon naught, times pi over 2. Okay, well, we can get rid of the pi's here. And now we have to take the integral of this monstrosity, and this is in our table of integrals. So from here, you should be able to do this. We can find our table of integrals, and this is negative h squared plus rho squared, rho prime squared, don't forget, to the power of negative 1 over 2, evaluated from 0 to a. Well, when you plug in a for, I guess we can just do this. Let's only do this part. This is going to be negative h squared plus a squared, power of negative 1 over 2, minus negative h squared plus 0 squared to the power of negative 1 over 2. So this becomes negative 1 over the square root of h squared plus a squared plus 1 over the square root of h squared. That's 1 over h. right? So what are we left with? We are left with the z component of the electric field is equal to rho s0 divided by 4 epsilon naught. I guess actually it would be 4 times 2, so 8. We can rewrite this as 8. Times, we put the 1 over h in front. Yeah, 1 over h in front, I think, right? Divided by the square root of h squared plus a squared. And that is volts per meter for the z component. That is our answer. I hope this is right. It should be right. I mean, I'll check real quick. Perfect. Okay, that's correct. I just need to make sure because I'm kind of do this by hand. I should probably have the answer sheet next to me, but it is what it is. Part B now. Now we're looking for, I believe, the x component. So now we're going to do the same thing. We actually have done a lot of the hard work already. But now we are just going to take this electric field, large electric field, with all of the components and shrink it down to only the x component. So now what we're going to have here is we're going to have the negative integral, double integral. The bounds are the same because we're still integrating over the same field. But now we're only worrying about the x component. And you might have asked, why did I put the negative here? Well, because the x hat has a negative. So we're going to throw that to the outside. We're not going to worry about it. Rho s0 divided by 4 pi epsilon naught of, what is this? Well, this is x prime. Let me put this actually on top. X prime divided by rho prime squared plus h squared. This doesn't change. Times rho prime d phi prime d rho prime d phi prime. Let me make that a little better for y'all. Okay, now what do? We have this x prime. We can't just take it out to the front because x prime actually will depend on some variables. So what do we do? Well, we need to figure out what x prime is. What is x prime? Let's draw our semicircle here. We know it goes from, my goodness, these semicircles are terrible. We know it goes from pi over 2 and 0 between there. We have a phi here. What is this? Well, x is this axis and y is this axis. If we connect and create a triangle where this is rho and this is x, what is, oh, I guess, and this is phi, what is the x component? Well, x prime, I'll label these primes because we're on the charge, x prime is actually equal to rho cosine of phi prime. Again, these are primes. So here we go. We found our x prime in terms of rho prime and cosine and phi prime. Perfect. It's all we need to be able to solve this problem. Because now we can substitute that value in for x prime. Okay, you know what? We're going to substitute this here. All right, so now let's rewrite this integral, and let's take out anything that we don't really need. So again, rho s0 is a constant divided by 4 pi epsilon naught, all constants, divided, or taking the integral from 0 to pi over 2, we're going to do the d phi prime. Well, now there's a cosine phi prime, so we need this. We're going to integrate over from 0 to pi over 2 of this cosine phi prime function, and we're going to then multiply it by 0 to a of phi prime. Oh my gosh, we have another phi prime, so we can say phi prime squared divided by phi prime squared plus h squared to the power of 3 over 2 with respect to phi prime. Now, this might look very similar, and of course it does. But there are some caveats here that you have to be able to know how to use that table of integrals that he gives you. Otherwise, you won't be able to solve this problem throughout, honestly. Unless you have I guess maybe the new calculator, I'm not sure how that works. Cosine phi prime, what is that? Sine phi prime, sine evaluated from pi over 2 to 0 is just 1, so we don't have to worry about that. negative s naught, negative rho s naught, 4 pi epsilon naught times 1, right? Because sine of pi over 2 is 1, sine of 0 is 0, right? So we don't have to worry about it. And now we have this one. This is also in the table of integrals. And what we can then say is, I'm going to write this down because it's very, very long. Negative negative rho prime divided by the square root of rho prime squared plus h squared plus natural log of rho prime plus the square root of rho prime squared plus h squared, all evaluated from 0 to a. So for every rho squared or rho prime, you're going to plug in a. So now we have negative s naught, 4 pi epsilon naught, negative rho prime, I forget, negative a, over a squared plus h squared, plus natural log of a plus the square root of a squared plus h squared. Minus, we cannot forget this, minus, well, when you plug in a 0 for rho prime, you get 0 plus, so we're going to say minus natural log of, this is 0 plus the square root of 0 squared plus h squared. What does that all become? Well, this all inside becomes h, the square root of h squared, which is h. So now what we have is the electric field in the x component is equal to negative rho s naught divided by 4 pi. Again, this is very long, so I'm just going to write this out. Hopefully I didn't miss anything. I feel like this is seeming pretty fair. If I did miss something, I'll go back and fix it, but this is from what, like, this is what I'm getting when I'm doing this, like, straight just work. So hopefully this makes sense. I'll check this real quick. All right, bet. That's right. Okay, so now we've done part B. Hopefully this made sense. I think the hardest part here is really remembering that x prime you can't just take x prime out. You have to know that x prime is rho prime cosine phi prime. Everything else, once you're able to get this integral, can become easier. Now, part C is a little bit odd. Honestly, symmetry is so weird. I mean, I haven't been to very many of his classes, so like I don't know if, symmetry was taken as a big point, but from the past exams I've seen, it's a pretty big point that will most certainly be on the exam sometime. But here, it says, without doing any calculation, how is e of x related to e of y at the point 0, 0h? Okay, so this is a little bit weird, I will say. The way you're going to do this is you're going to use symmetry. What do I mean by use symmetry? What I mean by this is the charge is actually symmetric about what? What line is it symmetric about? It's going to be symmetric, since it's in the xy plane, it's going to be symmetric about the y is equal to x line. What does that tell us? Symmetric about the origin, or sorry, symmetric about this y is equal to x line. That means y is equal to x. So the y component of your electric field will be equal to the x component of your electric field as well. So E of y is equal to E of x. Now, if anyone else has any like other explanations as to why this is true, please leave them in the comments, because I just thought about symmetry because, his answer literally says bisymmetry, but he never explains what he means by bisymmetry. So I kind of took it upon myself to assume this is why, because there's symmetry across the line y is equal to x, since we're in the xy plane, and we are integrating, or the phi goes over from 0 to pi over 2. If it went from x to negative x, it would be at the symmetric about the or symmetric about the y-axis, I guess, right? It goes from x to negative x, or negative x to x. Anyways, hopefully that made sense. It's symmetric about the y is equal to x line, so it has symmetry, and e of x component is equal to the e of y component. Honestly, if you can do this math, don't worry about that other symmetry stuff. It'll come in different problems, which we'll go over. Anyways, hopefully this helped. If y'all have any questions, please comment or reach out to me. If you have any other ways to do this problem, I know there are multiple ways to do this problem. You don't have to do my way. This is just the way I've done it for the past couple of weeks now. So hopefully this helped, and good luck on these problems.